Hey there, algebra buddies. Here we are, lesson 4, talking about exponential graphs. So here, instead of doing all the different parent functions and different families of functions, we are going to focus on our exponential family. And there's some really great applications that we can use that we'll cover over the next few lessons dealing with exponential graphs. But what we're used to dealing with is linear equations, and let's discuss the difference between linear equations and exponential equations. Well, a linear equation is an equation that has a constant rate of change. The linear equation uses the generic form y equals mx plus b. We've been spending a lot of time graphing lines, so we understand and we are familiar with y equals mx plus b. A linear function with the slope here being m has a constant rate of change. Let me try to spell that a little better. Okay, constant rate of change. What that means is the y values increase, no, because they could decrease. We'll say y values change by adding or subtracting. An exponential graph is going to be obviously different. An exponential graph is a graph that goes by the general format a times b to the x. The exponent is sometimes written inside the parentheses. That's okay. It's the same either way. An exponential graph has y values that change by multiplication. Now, if you multiply by a fraction, then it looks like division. So when you see in the table the y values change by multiplication or division, then it is an exponential graph. If the y values change by adding or subtracting, it is a linear graph. So that's one thing that you're going to have to be able to notice and distinguish between two given tables. So let's try this. When you first look at this table, you see it goes from 4 to 8, and you're thinking, you just add 4. But maybe you multiplied by 2. I'm not sure which one it is. So let's look at the next one. From 8 to 12, 12 to 16, 16 to 20. What keeps happening over and over and over? The y values change by adding 4. That makes it linear. So whenever the y values change by adding or subtracting the same number repeatedly, that's a linear equation. Let's try the next one. It goes from 15 to 30, and you're thinking, we just add 15, or maybe it doubles, times 2. Let's keep looking. 30 to 60, 60 to 120, 120 to 240. This seems like we are multiplying by 2. So the y values change by multiplying by 2, and that makes it exponential. Let's try the third one. It goes from 16 to 8, and you might be thinking, okay, well, that's just subtracting 8, or maybe it's a half. You keep looking to find the pattern, and we're noticing that it keeps going down by a half. So the y values change by dividing by 2, but we are multiplying by 1/2. Dividing by 2 means multiplying by a half. That means our equation is exponential. So on a table, that's how we know. As far as a graph goes, a picture, if you are ever asked to pick out the picture of a line, pick the picture that looks like a straight line. If you were ever asked to pick a picture of an exponential graph, you have two options. You have one that could curve up, get very close to the x-axis, but then curve up, never actually touches the x-axis, but it gets close. Or the other potential is that it's an exponential decay, in which case it would curve down. But those are both exponential growth or exponential decay. They're both exponential equations. To figure out whether your graph would be an exponential growth or an exponential decay, you would look at the value that has the exponent. This is called our common ratio. That is the number that is used in the table to change the y values. So when I said the y values change by multiplying by 2, in that particular example, the common ratio is 2. And then in the third example that we did, because the table is decreasing by multiplying by a half, the common ratio is 1/2. The other piece to this, the a value here, the a value represents our initial or starting value. Okay? If the graph does not have any vertical or horizontal shifts, that a value is the y-intercept. If it's shifted, obviously, it would be a little bit different. The shift would come if we had a plus number after this equation. If we added an extra 2 or an extra 5 or an extra 10, that would slide or shift the whole graph either up if it was positive or down if we were subtracting a number. That would adjust our y-intercept a little bit. But back to this common ratio. Our common ratio will tell us whether we have a graph that is increasing, like the exponential growth, or whether we have a graph that is decreasing by the exponential decay. And this is kind of logical how we tell the difference. If the graph is increasing, that means we have to be multiplying by a number that will make our values bigger from one to the next. So that is when our b value is greater than 1, we get a growth. An exponential growth is when our graph will increase from left to right. If the value we are multiplying by over and over and over is a fraction or decimal in between 0 and 1, similar to our third example at the top, we kept multiplying by 1/2, so our y values decreased. That will give us an exponential decay. So our exponential decay will be found when our b value, our common ratio, is between 0 and 1. Our graph would decrease from left to right. Now, for both of these examples, our graph will never actually touch the x-axis. It gets close to it, but never actually touches it. The value on the graph that your curve approaches but never reaches is represented by a horizontal asymptote. That's how you pronounce it. Spelled weird, but it's pronounced asymptote. The asymptote is the value on the graph. It's the value that the function approaches but never reaches. Never exactly gets there. So for both of these values, the exponential growth and the exponential decay, the y values get very close to 0 but never actually reach 0. It's kind of like the idea of cutting something in half and then cutting the half in half and then half in half, keep cutting it in half. Theoretically, you never run out of something to cut in half. It doesn't ever go away. What happens in real life is it gets so small you don't notice the difference, but technically there's still something there. All right, so let's do some graphs. Y equals 3 to the x would be the same thing as f of x equals 3 to the x. So what we're doing here is we are going to take 3 and apply different exponents to that 3. So to fill in our table, we'll do -2, -1, 0, 1, 2, 3. I'm going to do some of this without the calculator just to help us review what happens with negative exponents. So what we're going to do is take our x value and use it as an exponent. So if I put in an exponent of -2, a negative exponent mm, reminds us or tells us that we should be taking the reciprocal. In other words, we are going to take this value of 3 to the negative second, turn it into a fraction by putting it over 1, and the negative exponent flips this fraction and switches the numerator and the denominator. So instead of 3 to the negative second, we can rewrite it as 1 over 3 squared. And 1 over 3 squared means 1 over 3 times 3, or 1 over 9. Now if we do 3 to the negative first, we would flip that to make it 1 over 3 to the first. So that's 1/3. And then anything with an exponent of 0 is always just 1. And then 3 to the first power is 3. And then remembering what we talked about with the table of values on the previous page, an exponential graph will have the y values increase by multiplying the same number over and over and over. So if we know that the common ratio is 3, then we should know that we are multiplying times 3 over and over and over. 1/9 times 3, 1/3 times 3, 1 times 3, 3 times 3, 9 times 3. Oops, 9 times 3 is 27. Let's plot our points and see what our graph looks like. I'll skip the fractions for now. Let's just plot the whole numbers because those are easier to graph. We see a pattern in the dots and we can connect them for a graph. So there's 0, 1, 1, 3, 2, 9, and we are already off the page. And then we can approximate where 1/3 is, 1/9, and these values get so close to the x-axis, we really can't separate the x-axis from our actual graph, but we never cross the x-axis. Technically, we never touch the x-axis either. But once we're graphing this, it's going to hit these points and grow really quickly and get really steep really fast. So that's our exponential growth because our b value in our equation is greater than 1 and the graph is increasing. The horizontal asymptote, that means the value that the graph approaches but never actually touches, is right on the x-axis. Our y values get really, really super close to 0, but never actually reach 0. So our horizontal asymptote is at the equation y equals 0, which is the x-axis. And we know this because our table keeps getting reduced by 1/3 going backwards. And like I said with the 1/2, you keep cutting it in half, it never fully goes away. You keep dividing it by 3, it never fully goes away. The domain for our graph, domain and range, is simply measuring how far to the left this graph will go and how far to the right this graph will go. Well, this graph comes from negative infinity, sideways from the left, and goes to the right forever, so up to positive infinity. So our domain are the x values left to right where the graph is drawn. If I had enough paper, I would draw it to the left forever. If I had enough paper, it would slowly go to the right forever. Our range would be the y values. So the lowest y value and the highest y value. Now, our graph gets really close to that x-axis, almost to where y is equal to 0, but never actually reaches 0. So we represent that by a curved parentheses next to the 0, saying it never equals 0, but gets super close. And our graph, as you can see, goes up the page vertically forever. So it goes up to infinity. So that's an example of an exponential growth by a common ratio of 3. Let's do an exponential decay with a common ratio of 1/3. So what we're going to do is use the same x values, -2, -1, 0, 1, 2, 3. Now let's try to do this without the calculator and see how far we can get. I think we can go all the way here. This equation doesn't quite exactly look like what we talked about on the previous page with a and a b value both. But it's subtle, but it's there. It's just hard to see because it's not written. This technically is saying 1 times 1/3 to the x. So our starting value, our starting amount would be 1. That's the y-intercept. And our common ratio is 1/3, so that means from one point to the next point, I multiply times 1/3. So 1 times 1/3 is 1/3. And then times 1/3 again technically makes it 1/9. And then times 1/3 again would technically make it 1/27. Now let's do this going backwards, shall we? Instead of multiplying times 1/3, working backwards, it's multiplying times 3. So what we see here, multiplying by 1/3 is actually like dividing by 3, dividing by 3, dividing by 3. As the x values get larger, the y values divide by 3. So if we think backwards, the opposite of dividing by 3 while the x values increase would be multiply times 3 while the x values get smaller. So then -1, it would be up times 3. -2 be up times 3 again. Now we got some plot points we can plot. So -2, we're at 9. -1, we're at 3. 0, 1. And then 1/3, 1/9, 1/27. And again, we get so close to that x-axis, we really can't see the difference between one side and the other. And our graph gets super steep, comes from being super steep pretty quick. And there's an example of our exponential decay because our b value is a fraction in between 0 and 1. And another way to look at it is our graph is decreasing. From left to right, we see our graph is decreasing. Our horizontal asymptote, by the way, is in the same location as it was for the above graph. It's going to be right along the x-axis, which is the equation y equals 0 again. The domain and range, however, are going to stay the way they were. Domain still goes left and right forever. And the range still gets close to 0 without hitting 0, and up comes from a positive infinity. All right, I hope we're doing good. Now we're going to do an application. All right, word problems and applications for exponentials go all the way from banking to population growth to Riley using an Uber-style company for when she goes on vacation this summer. Company 1 has a plan that charges an initial price of $3 plus $2 every mile. Company 2 has a plan that charges an initial price of $1 and the cost doubles every mile. We are going to generate two different equations, one for each company, and then we'll compare them using the graph and some plug-in values. So we have company 1. Company 1 charges $3 to start with plus $2 every mile. So the total cost is an initial value or fee of $3 plus $2 for every mile driven. So we have miles driven as our x value, total cost is our y value on our graph. So we have total cost here and miles driven here. Company 2, let's see, I'll pick a nice blue. Company 2 has an initial charge or price of $1, so their cost is $1, and it doubles. So that means we multiply times 2 every mile that's driven. So what we're going to do now is graph these two functions, these two equations on our graph. The linear equation is going to be a little bit easier to graph. We start at a y-intercept of 3, and it goes up $2 every 1 mile. Up $2 every 1 mile. So up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. This is probably annoying to you, but it's sometimes fun to say. Almost like a song. Up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. Connect the dots. That is company number 1. Our exponential graph, company number 2, starts at an initial fee of $1 and then it doubles. So that means after 1 mile, instead of $1, we have to pay 2. And then after that, instead of 2, we go to 4. And after that, we go to 8, and then 16, and then we're off the page. So let's connect those dots nice and carefully. I kind of missed that. Let me redo that. There we go. That's a little better. All right, so there's our two graphs drawn on the same graph, and this is company number 2. Part C here says most of Riley's trips are 4 miles. Which company should they use if they're only going to drive 4 miles? So here's what we're going to do. We're going to take our equations, we're going to do a little bit of algebra work, and we're going to figure out which one's a better deal. For company 1, starts with $3 and it adds $2 every mile. If we're doing 4 miles, we put 4 in for the number of miles. Doing the algebra work here, we'll take our 3 and add it to 2 times 4, which is 8. So when we're done, our total cost is 11. $11 for a 4-mile trip. With our company number 2, our cost comes from an initial price of $1 and then $2 per mile for 4 miles. So you can go to your calculator. We can type that in. 1 times 2 to the 4th. 1 parentheses 2 exponent of 4. It's going to tell us it's $16. So which one's a better deal? For going only 4 miles, it will be company 1. Company 1 is less expensive if we're only going if we're going 4 miles. Now let's try going a 2-mile trip and see which one's a better deal. So we take company 1, initial fee of $3 and $2 for every mile for 2 miles. So that means we will do 2 times 2 and add them together. So for a 2-mile trip, company 1 costs $7. Let's figure out company 2. Company 2 has an initial price of $1. It doubles every mile across 2 miles. So then 1, 2 squared is 4. Hey, look at that. Company 2 would only be $4. So if we're going a shorter distance, company 2 is less expensive. Now, how is that shown on the graph? I'm glad you were thinking that and wondering how to ask that because I'm doing a video. Well, I'm just that good and knew that you were thinking that, which I know you weren't thinking that. But on the graph, anyways, here we see a little bit of space in between the two graphs. They eventually meet, and then they kind of switch which one's above, which one's below. That tells us which one's more expensive and which one's less expensive. So on our axes, here's 1 mile, 2 miles, 3 miles, 4 miles, 5 miles. Somewhere in between the 3rd and 4th mile, company B becomes more expensive than company A, or company 2 becomes more expensive than company 1. Company 1 is more expensive for doing a short trip of 1 mile, 2 miles, or 3 miles. For 1 mile, 2 miles, or 3 miles, company number 2 is less expensive. But as soon as we get to 4 miles or higher, now company 1 is less expensive, and in company 2, the price jumps quite a bit. So there we have it. There is lesson 4 all done in a nice under 25-minute package. I hope you guys are excited about all this great exponential stuff. When it's time, go ahead and enjoy lesson 5 and 6 and 7 and the rest of it, and have a nice day. Stay safe.